This video is going to go through our polar review. So looking at our upcoming quiz, essentially the quiz can be divided into three main topics. How we work with the pre-calculus side of polar, how we graph them, how we write the coordinates or transfer between coordinates, the calculus part, which is the derivatives, and then finally the calculus part, which is the area. So that's what this video is going to go through and do those three different things to prep you for each topic that you're going to see on your quiz. So one of the first topics that's going to be on the quiz, it's the first couple multiple choice questions, and it's the first short answer, is being able to graph or being able to successfully name points or come up with different ways to name points. So in this review, it looks a lot like what we did on day one. We are going to plot these points in polar and then talk about different ways that we can name the same points. So for A, when we are looking at 3 pi over 3 is the angle. We actually use that first. And then 3 is my r value, how far out I go as far as how many circles out I go. So pi over 3, I'm going to have, this is my pi over 4. My pi over 3 is going to be right here. And I am going to go out 3 units. So let me get my pen. So I go out to pi over 3, and then I go 1, 2, 3 units. And there is A. And then for then B, we are going to pi over 2, which is up here, but I'm going backwards, so I'm going to go down from the pole 2 spaces, and that is going to give me point B. Letter C is going negative 3/4, so now you're going in this direction, negative 3/4, which is going to take you over here. But then from there, I'm also working in the kind of the backwards r, the negative r value going back 4 from the pole. So 1, 2, 3, 4. And there's C. And then finally D. D has an angle of 3 pi over 2. However, if you look at the r value right away, you'll realize that we're not extending at all from the pole, which means no matter what the angle is, my D value is going to be right in the center, which we call the pole of the polar graph. The other skill that you should be able to have is come up with other ways to name. So the one that I mentioned was A. If I take this point A, think of what are other ways that I could end up in the exact same spot. Well, one option would be for me to go an extra revolution around. So instead of going just pi over 3, I could add 2 pi on top of that, basically cycling through a whole way around again, and I could go to 7 pi over 3 and keep my radius the same. Another option would be to go in around to the other side, kind of across from where A is, and then use a negative r value to work backwards. So if I go on the other side, I'm going around all the way to 4 pi over 3. But then I want to go in reverse 3 spaces, so I could say negative 3, 4 pi over 3. Other options is I could go in a negative direction. I could go around, I could go negative 5 pi over 3. And to 3, I could go in the negative direction, like a negative 2 pi over 3, and then go backwards. So there's many, many ways. I mean, really infinitely many ways. If we keep revolving around over and over and over again, I am never going to ask you to do more than 2 other ways. So I just want to give you some options of what you could use there. For the derivatives, mainly the goal is that you can come up with ways that we write our x and y. We can find the dy dx by using a lot of product rules and then use your unit circle and your calculator to come up with the exact slope at a particular angle. So for this one, it gives you our curve. R is 3 sine 2 theta, and we want to find the slope at the particular angle, pi over 3. And I'm going to take you through this one, just kind of what you could do without a calculator, and also talk, obviously your calculator is a huge way to check your work and especially get through some of the things that are a little uglier. So the first thing I want to write down is my x and my y. X is r cosine theta, so it would be 3 sine 2 theta cosine theta. And y is r, so still the 3 sine 2 theta sine theta. So when I find dy dx, it's dy d theta, so the derivative of the y piece using a product rule, divided by dx d theta, which is the derivative of the x piece using a product rule. So we've got, we'll start with the dy d theta. And the biggest thing is just making sure you get the right one on top. That's the easiest thing to mess up. So with the y, I'm going to take the product rule of this particular line. So first times the derivative of the second is going to give me 3 sine 2 theta times the derivative of sine, which is cosine, plus the second times the derivative of the first, so the second is sine. The derivative of 3 sine 2 theta is going to be 6 cosine 2 theta. Doing a quick little chain rule there, times the original sine function. So that's my dy d theta. Dx d theta in this one is going to be doing the same thing, but with the x equation, using my product rule again. So first times the derivative of the second. The derivative of cosine is going to be negative, so I'm going to put that negative first. So negative 3 sine 2 theta. Derivative of cosine is sine with the negative that I put out front. Plus the second times the derivative of the first. So cosine times the derivative. We already said the derivative of 3 sine 2 theta is going to be 6 cosine 2 theta times cosine. At this point now, I'm going to go back everywhere I see a theta and put in pi over 3. Sometimes you'll run into problems where you could really simplify things a lot. This one doesn't have that happen. If you want to simplify, you'd have to get into double angle identities. But if there's something obvious, if there's like terms that you can combine, or if you can use an identity, like if you can take sine squared plus cosine squared equals 1 and replace the sine squared plus cosine squared with that, that can really simplify things. This one really, there's not much other than a lot of just plug and chug. So I'm going to put a pi over 3 everywhere, and I'm going to try to go through kind of quickly and show you that. So when I put a pi over 3 into the sine 2 theta, it's going to be taking the sine of 2 pi over 3. The sine of 2 pi over 3 is going to be the same as the sine of pi over 3. It even has the same sign. So it is radical 3 over 2. The cosine of pi over 3 is a half. Then plus 6 times the cosine of 2 pi over 3. Cosine of 2 pi over 3 will be negative. Cosine is negative in the second quadrant. It will be negative a half. And the sine of pi over 3 is radical 3 over 2. On the bottom, I'm going to have negative 3. Sine of 2 pi over 3, as I said, is radical 3 over 2. Sine of pi over 3 is another radical 3 over 2. Plus 6 times the cosine of 2 pi over 3, as we said, is negative a half. And the cosine of pi over 3 is positive a half. At this point, I'm going to simplify. Again, you could do a lot with your calculator, but I want to show you this one gets really neat without really relying on a calculator that much. Obviously, it's a lot of arithmetic. The first fraction, I'm going to have 3 radical 3 over 4 minus, because I have a negative in the next term, 6 times a half is 3, so I get 3 radical 3 over 2. On the bottom actually gets a little simpler. The radicals go away, because right away you see that you have a radical 3 times a radical 3. That's going to be 3 times the negative 3 that's in front, all over 2 times 2. So I get negative 9 over 4. And then the next one, it's negative. I have 6 times a half, which is going to be 6 times a half is 3, 3 times a half is 3 halves. At this point, if you want, you could clear fractions. If you want to just kind of work with the top and work with the bottom, that's fine too. That's what I'm going to do. I'm going to multiply this one by 2 over 2 just to get a common denominator. So I have 3 radical 3 over 4 minus 6 radical 3 over 4. And on the bottom, if I get everything in fourths, I'm going to have negative 9 fourths minus 6 fourths. Everything's in terms of 4, so I can cancel all the 4s. Essentially just multiply everything by 4, top and bottom. So I get 3 radical 3 minus 6 radical 3. That is negative 3 radical 3. And I have negative 9 minus 6 is negative 15. The negatives will cancel. Your final answer, in a very exact form, is the radical 3 over 5. As a decimal, if you were working with your calculator and doing more as a decimal, you should have got a 3 decimal places as 0.346. Which would be the equivalent answer. You can also check this on your calculator. If this is a situation where you're allowed to use a calculator, you can graph your polar function, and if you use the calculate menu, it will actually find the dy dx. Now, on a test or a quiz, I am going to ask you to show me the derivatives, how you are working it out by hand to be comfortable with that, but I would definitely recommend going to your calculator and checking your work, because a lot of times I had an issue with a minus sign when I started going through this one, and my calculator showed me that I need to go through and fix it, and I was able to find my mistake, and that really helps. The last piece, and definitely the most common, is area. And I'm going to do 2 area ones with you. I tried to pick ones that were the most common as far as what we've seen on AP tests and what you're going to see on the upcoming quiz. So this first one is an area of one that is inside a circle but outside a rose curve. We did one like this on class that was from an old AP test. We're going to do one exactly like this on the quiz. So I figure it's a very authentic type of problem. First thing you want to get is a visual. So obviously r equals 3, we all know, is a circle centered at the pole, radius of 3. r equals 2 cosine 3 theta. You should know it's a rose curve. You should know it's a rose curve that has 3 petals, but you can definitely go to your calculator to get a more accurate picture. I can just draw what you would see, but at this point you should be pulling it up on your calculator as well. This is what it looks like. And the question is asking you to find the area that's inside the circle and outside the rose curve. So thinking of it like this. What we need to do then is find, obviously, the entire area of the circle, which is not a calculus problem. It is just using geometry, and then subtract the area of the rose curve petals, which is where the calculus comes in. So that's how I'm going to start it. I know that my area of my circle is pi r squared. So I know my circle has an area of 9 pi. I want to subtract the area that is contained in all 3 petals. So the first thing I want to do is I want to figure out some boundaries here. So I'm going to look at when 2 cosine 3 theta equals 0. That gives me what was called the tangent to the pole and gives me some good starting points for my boundaries. So I really want to know, when does cosine equal 0? Cosine equals 0 at pi over 2. So that means I want 3 theta to equal pi over 2, which means that theta has to equal pi over 6. And when you look at a picture on your calculator, it's a pretty good representation of what's happening, and I like to, if I'm allowed to use my picture, I like to look at the graph and kind of see, does that answer that I'm getting make sense? And it definitely can see where that would come into play. So you have a couple choices. You can either find the area of one petal and then triple it. And if you found the area of one petal, you could look at the petal that I've already started talking about on the right side and say, well, I'm going to go from negative pi over 6 to pi over 6. I actually went even simpler than that. I decided to find the area of half the petal, so this little piece right here. And then when I get that answer, I would multiply by 6 because there's 6 half petals there. So that was my setup. I did 6 times a half, and the half comes from the formula, of the integral from 0 to pi over 6 of my r, which is 2 cosine 3 theta, and make sure when you're putting in your calculator you do square the whole thing and not just the angle. Little things that you want to watch. So the 6 times a half will give us 3. Then I use my calculator, make sure you're in radian mode. You get an area of about 1.047. I immediately multiply by 3. And the interesting thing here is you actually get an area that is equivalent to pi. If you were to do this problem by hand, it would be a mess because of all the trig and identities you'd have to use, but you would get pi when you were all said and done. So we want to know the total area that's in that shaded region, so I'm going to take 9 pi minus this answer, minus pi, it ends up being, and you get an answer of either 25.132 if you truncate, 25.133 if you round, or if you were work it out exactly by hand, it is exactly 8 pi. That one is very similar to the very last question that you'll see on a quiz, and very similar to what you've seen on previous AP test questions. The last one is comparing area that's formed with a cardioid and a circle, another really common piece that we see on a lot of AP tests. So first thing, we need the visual. Now I will say with this one, when you graph on your calculators, when I graphed on my calculator, I did a zoom trig. It's so small that it would almost be a little better if you kind of blew it up, either zoom in a little bit more, or just when you draw the picture, draw it a little bit larger so you can really see what's going on. This is what you get. Your cardioid looks something like this. Has that kind of point right on the pole. And then your circle, and it only has a radius of a half, so it is very small. But I'm trying to kind of blow it up so you get to see it a little bit better. So the question wants to know, what is the area that's inside the cardioid and outside the circle? So let me shade in what you're actually finding. I thought this one was a little bit more challenging than the last one, just to give you a gauge on difficulty. So the first thing that I did is I decided, again, to use symmetry, but I do want to find where these intersect because I need that kind of that stopping point there. So I set 1 minus sine theta equal to a half. Obviously, you could use your calculator to do this as well, but it is good practice to get comfortable with things like boundaries or things you should be able to do without a calculator. Subtract 1, we get negative a half, divide by a negative, so we want to know when does sine equal a half, and that happens at pi over 6 and 5 pi over 6. And that is what these intersection angles are. Pi over 6 here, 5 pi over 6 here. What I did is, at that point, I decided I'm going to look at what's under the cardioid just on the right side. So just going from like here to here, and get that information, and then I'm going to subtract the circle piece that's contained inside. So let me write what I just said and then explain it again. I decided to start, I went from negative pi over 2 to pi over 6. Because if I just go around like this and just work with the cardioid, that's going to give me everything. And then I'm going to subtract out what is not there. So we'll start with that. We have 1/2 integral from negative pi over 2 to pi over 6. And I'm looking at what's inside the cardioid, so that would be the 1 minus sine theta, and that whole thing is squared. Now, I am just looking at the right side, so I do need to double this because we are looking at that region that is on both sides. So that too will get rid of the half. I'm going to go to my calculator, make it do all the work, and I get an area of 4.657. It went on further. I did store that number in my calculator, but I'm not writing all the digits for you right now. Then I want to get rid of the stuff that's in the circle. So let me use a different color just so you can see a little bit more what I'm referring to. What I don't want to include that's part of the cardioid, but it's also part of the circle, is I want to subtract out what is in red. So a couple ways to do this. Instead of doing it geometrically, I decided to just stick with more of a calculus-based approach here. So I want to subtract the integral from negative pi over 2 to pi over 6 again, but this time what's in the circle. So my circle has a radius of 1/2, so it would be 1/2 squared, or 1/4. Now I didn't put anything in front, but we know in the formula we have 1/2, but we also know that there are two sides that I want to get rid of, so if you kind of want to write that and then immediately cross out that they cancel, that is fine. When I took 4.657, which was that entire right side, and then I subtracted out that piece that was in the circle, the red piece that's in the drawing that you're looking at right now, I get an area of 4.1335, and you're welcome to round that up to 4.1334, 4.134, or leave it as 4.133. Rounded or truncated would work out perfectly. So this video, I know it's a little longer than maybe some, gives you an idea of all the things that you should be able to do polar-wise. You should be able, again, to graph, to rename points, to take those equations, the r cosine theta equals x and the r sine theta equals y, to convert from different forms. You should be able to find derivatives and find slopes at particular values, and then you should be able to find area either enclosed by one curve or enclosed by two different curves.